In this video, the third in the series, we'll look at specific applications of entropy to special processes. We start with a reversible isothermal expansion, and it is important to note that this is reversible because remember the definition of entropy depends on the heat transfer in a reversible process. So because this is a reversible process, we don't have to devise an alternative scheme to do our calculation. In this situation, again, we go back to our definition for entropy. ds is equal to dq reversible over t, and we need to figure out for this process what dq reversible would be. Now, of course, if we assume an ideal gas, we know that for isothermal processes there is no change in the internal energy, and that means that dq is equal to negative dw. And since dw is equal to pdv, and also since this is a reversible process, we're assuming that the external pressure is infinitesimally close to the internal pressure, then we have the situation where dq is equal to nRT over v dv. Now, if we do the substitution for our definition of entropy, we'll note that because dq is equal to nRT over v dv, we make the substitution for that above. And then we simply divide that by T, get the overall change in entropy that's occurring in our process. So we end up with delta S being equal to nRT over V T. Now again, remember that we have the situation, and just to remind you that this nRT over V is equal to pressure, and so we have again pressure dV divided by T as indicated by the definition of entropy. So if we integrate this expression, of course, we end up with delta S as being equal to nR natural log of V2 over V1. Where, of course, the T's cancel out in the integration, so that if you go back and take a look at our discussion of work in an isothermal reversible expansion, there's a subtle difference, a slight difference between the equation for work and the equation for entropy. The equation for work in this particular case was very simply just W is equal to negative nRT times the natural log of V2 over V1. So there's a slight difference here because the temperature cancels out, and also we have a difference in sign. Now, if we have an expansion where the final volume is greater than the initial volume, that means that V2 over V1 is going to be greater than 0, and that means that delta S is going to be greater than 0. So for the an isothermal expansion, that's going to be accompanied by an entropy increase. For an isolated system, of course, if we think about a situation where we have a gas confined to a particular container and we open the container up, we know that the spontaneous process is going to be the gas expanding from the container into and to the outside of the container. So this is perfectly consistent with our concept of the second law. Now, what about an irreversible process? Because remember, we said this was specifically the example that we might use for a reversible isothermal expansion. For an irreversible isothermal expansion, of course, we need to devise a pathway that would be reversible, and what we would devise is exactly what we have just calculated. So when we have an irreversible isothermal expansion, the calculation for delta S is going to be the same. We get the same equation. Delta S is equal to nR times the natural log of V2 over V1. And that's all we really need to know. So for any isothermal expansion, we can calculate delta S with this particular expression. Okay, so let's look at the reversible adiabatic process. Again, delta S is equal to dq over t, so we need to figure out what dq reversible would be. And what is that for an adiabatic process? Well, dq reversible is equal to 0. By definition, adiabatic processes have no heat transfer. And therefore, delta S for a reversible adiabatic process is equal to 0. Well, that's simple enough. All we need to know is if it's adiabatic and reversible, delta S is equal to 0. One has to be careful here, however, because if it's irreversible, it's not going to be equal to 0. We get a different result for the irreversible adiabatic process. So how do we do that? Well, if we have an irreversible adiabatic process, now we have to come up with a reversible path to get us from the initial state to the final state before we can calculate delta S. So in this case, we'll talk about just a very simple process. In the adiabatic, irreversible adiabatic process, we go from initial pressure, temperature, and volume to a final pressure, temperature, and volume. All three will change during the irreversible adiabatic process. So we will then devise a reversible set of steps to get us from the first state to the final state. So the first step is going to be one where the volume is held constant. That's called isochoric. And in that situation, we're going to allow the temperature to change to the final temperature with the volume held constant. So at the end of this first step here, the temperature is the same as it will be in our final step. The pressure will be some intermediate pressure that we'll call P sub A in this particular circumstance. Then our second step will just be an isothermal process that will allow the volume to change to the final volume and the pressure to change to the final pressure. So we're going to have two reversible steps. We're going to calculate delta S for each of these reversible steps, the isochoric step and the isothermal step, and then we're going to add the two together to get the total entropy change for this irreversible adiabatic process. So, step 1, isochoric temperature change. What's the work for an isochoric temperature change? Well, since it's isochoric and the volume doesn't change, the work is equal to 0. That's easy enough. And that means, therefore, that delta U is just equal to the heat transfer. And we know for a constant volume process that du is equal to Cv dt, Cv being the constant volume heat capacity. So we're going to take that expression for dq and we're going to plug it into our expression for entropy so that dq is equal to Cv dt, as we indicate here. So now we need to evaluate this by integrating both sides of the equation. And if we assume that the constant volume heat capacity is independent of temperature, we can pull that outside the integral, and so we end up with a simple expression: delta S is equal to Cv times the natural log of T2 over T1. That's simple enough. So that's step 1, which is the isochoric change. Moving on to step 2, which is the isothermal change. Well, we've already derived an expression from that earlier in this presentation, so that's just simply equal to nR times the natural log of V2 over V1. Same equation we derived earlier. So the total entropy change then involves just the sum of these two steps. We add the two together, and we get this for the irreversible adiabatic expansion. Now here's the thing. Because everything in this, the temperature and the volumes, are all functions of state, this expression is true for every process, regardless of whether it's adiabatic reversible, adiabatic irreversible, isothermal reversible, isothermal irreversible. We will get the same result. Recall, for example, that for the adiabatic reversible process, delta S would be equal to 0. Well, if you use this equation with the initial and final temperatures and the initial and final volumes of an adiabatic reversible process, you would find indeed that delta S was equal to 0 for this reversible adiabatic. If it's an irreversible adiabatic, we're going to find that it's not equal to 0. But you can rely on this equation for any particular process. You'll always get the correct answer. For an isothermal process, of course, T2 and T1 will be the same. So that means the ratio is of T2 over T1 will be equal to 1, and the natural log of 1 is equal to 0. So for an isothermal process, we just end up then with the second term in the expression, which again is exactly what we had for derived for an isothermal process previously. So this equation, again, will work regardless of the process that we are talking about. Now, if we have the initial and final pressures rather than the initial and final volumes given to us, of course we can always use the ideal gas law to calculate initial and final volumes if we have the pressures and the temperatures. But here is an alternative expression we can use when we have pressures instead of volumes, and we just simply derive this by using the ideal gas law, noting that the V2 over V1 was equal to P1 T2 over P2 T1, and making the substitution and then rearranging. When we do that, we will get the expression down here. It is important to note that in the pressure expression we're using the constant pressure heat capacity instead of the constant volume heat capacity, and that just simply comes from the fact that for an ideal gas, Cp is equal to Cv plus Nr. Okay, so let's talk about phase transitions. At the transition temperature, say the boiling point or the melting point, these are reversible processes. They are equilibria. Any time we have an equilibrium, and we'll talk about this in more detail in future videos, but an equilibrium corresponds to a reversible process. So at the boiling point and the melting point of a substance, we are undergoing a reversible phase transition. So in that case, we can just simply use the enthalpy change corresponding to the transition, the enthalpy of vaporization, for example, or the enthalpy of fusion, to give us Q, and that means that delta S is just simply equal to delta H for that particular transition divided by temperature. Now, it just so happens that for boiling liquids, we'll find that the vast majority of substances, liquids, have an entropy change for the at the boiling point, which is real close to this 85 joules per Kelvin per mole. This is called Trouton's rule. And again, this is for the majority of liquids. If you do this calculation, if you look up their enthalpies of vaporization at the boiling point, and you divide it by the temperature of the boiling point, temperature of course being in kelvins, then you will find that delta S is real close to 85 joules per Kelvin per mole for most substances. Of course, there are always exceptions. And so let's look at water and how it applies to water. At the boiling point of water, 100 degrees Celsius, with an enthalpy of vaporization as given here, we do the calculation for delta S, and we find that it's 108.95 joules per Kelvin per mole. That's quite different. It's much, much higher by a significant margin than the 85 joules per Kelvin per mole for Trouton's rule. Well, why is water higher? Of course, the reason that water has very unusual properties to begin with, as we've said time and time again, is this hydrogen bonding, the special properties of hydrogen bonding which give water its very unusual properties which make life possible on this planet, leads to a much higher value than expected for the entropy of vaporization at the boiling point. And you can make some sense of this in terms of our discussion of order-disorder. The hydrogen bonding gives the liquid a greater degree of order than would be otherwise expected in the liquid. So the change in going from the liquid state to the vapor state in terms of order is much greater than would be expected for other types of liquids. Okay, so this ends this particular video discussing various applications of entropy to different processes. In the next video, we'll look at some more applications and take a look at, for example, what happens to entropy changes when we look at irreversible phase transitions, those that, for example, do not occur at the boiling point or melting point of the substance.